Okay. Lesson 22, page number 104. Uniform motion problems and equal distances, and thirdly, similar triangles and proportions. Okay, so 3 different parts here. Fortunately, the similar triangles we've already done.
Yeah.
Because I taught how to do proportions the way I like to do them instead of the book, and now the book is going, oh yeah, you're kind of right, maybe we should teach it this way. So now they're teaching it the way I always teach it. So anyway, you already know how to do all that, so we really can kind of skip that part of it. Uniform motion problems. They have a statement in here that I absolutely hate, and I think it should be taken out of the book. It is probable that you will never encounter these kind of problems in real life. But we study them because it helps us develop useful problem-solving skills. Okay, so one of the worst things that you can write in a math book. If anybody says, Mr. Leiter, when will I ever use this? My answer is usually never.
Well, they're already thinking it anyway.
They're already, yeah.
I just address it.
How can they call it useful problem-solving skills if we're never going to use it?
Good question.
It's an
It's
oxymoron.
a-
Let's see.
It's problem-solving skills that you use every day, maybe not necessarily solving these kinds of problems, but it's kind of developing.
Actually, you use it to pass out.
That is true. You do use it to pass Algebra 2. It is very important to know. Some kids will ask, when am I ever going to use this? Friday on the test. There you go. So, anyway. Bottom of page 104, top of page 105. Uniform motion problems involve strategies about people or things that move at a constant velocity or speed, or at an average velocity. The uniform motion problems on which we will concentrate will contain 4 statements about things that are equal or that differ by a specified amount. How many statements? Each of these statements can be turned into an equation, and we find that these equations are easy to write if we use 4 variables. In this book, we will use subscripted variables, which is what we have been using. To solve uniform motion problems, we'll write equations about rate or velocity, equations about time, and equations about distances traveled. So we will be using this formula, D equals RT, or a variance of that formula. D stands for distance, R for rate, which means your speed, and T for time. Now, a lot of the times you're not going to be just finding distance. Some of the times they're going to be asking you to find rate. What does rate equal?
Distance.
Okay, how about time? What does time equal?
Distance over rate.
Distance over rate. So those are the 3 formulas that you use that have to do with distance and speed in time. Okay? We'll do acceleration in calculus. Where we're finding,
Or in physics.
we'll be finding double derivatives of equations, and yeah, probably not doing that in physics, but
We worried about derivatives and algebra.
we will not even think about the word derivative in Algebra 2. We won't even think about derivatives in college algebra or college trig. First time you hear the phrase where you have to do something with it, it'll be calculus.
Nice.
So, and derivatives aren't really too terribly bad. They're kind of scary to start out with, and it's like, oh my gosh, this is so easy. So. All right, so to solve uniform motion problems, we'll write equations about rate or velocity, equations about time, and equations about distances. Important. Since the distance equations are the most difficult to write, we will consider these equations to be the key equations, and we will write the distance equation first. So, using these equations here, those are the ones we're going to be putting first, and then we're going to be given enough information. We can just kind of plug numbers in and solve for the variable, and then we're done. Okay, a couple of the key things is, let's say that you have 2 people riding their bikes. All right, so Tim hops on his bike. He's at Fred Meyer, and he is riding his bike home. Okay, so that's the distance Tim rides his bike. Okay? Elias is also at Fred Meyer, and he is going over to Tim's house because Tim dropped his ice cream cone and Elias was really bad, so he's going to stop at short stop on the way and take him a new one. Okay, so Elias leaves an hour and a half later. How far did Tim ride?
Fred Meyer's to home.
From Fred Meyer to home. How far did Elias ride? Okay, so even though they rode at two different times, they both went the same distance. Okay? So that's one thing that we can say. We can say the distance that Tim rode equals the distance that Elias rode. What do we also know about the distance that Tim rode? Distance equals rate times time. I can also say that his speed times his time equals Elias's speed times his time. Does that mean they rode at the same speed? No. It just means that if you took their speed times their time, you'd get the same number. So for instance, if Elias rode his bike 20 miles an hour and it took 3 hours, how far did he go? 60. If Tim rode his bike 30 miles an hour for 2 hours, how far did he go? Okay, so they both went the same distance, it's just their times and speeds were different. But when you multiply them, you'll get the same number. Okay? So there's another way to write that Tim's distance and Elias's distance were the same. Speed times time equals speed times time. Okay, not only can we look at it that way, we can say that Adam gets in his car, he drives to Walmart, so that's to Walmart, picks up a new Barbie doll for his cousin Maggie for her birthday. He gets in his car and he drives back. What do you know about the distances to and the distance from Walmart? They're equal. Okay? So that's a key thing, is trying to figure out what you know is equal to each other. Sometimes those distances are equal, sometimes they're not. But you have to make them equal by adding or subtracting a number or something in order to make that the case. In this lesson, we're not going to do that. We're just going to make them all equal, and life is so much easier. So, let's look at Roger and Judy. Okay, so it is Sunday, and Roger makes this trip from here to here. Okay, that is the distance that Roger traveled. On Monday, Judy makes the same trip. Different day, same trip. So the distance of Judy. Distances are the same since they made the same trip. Roger traveled at 12 miles per hour. So the rate of Roger is what that says. Judy, the rate Judy traveled was 20 miles per hour. Her time was 2 hours faster or less than Roger's time, because she was going faster, so she got there sooner. So Judy's time was 2 hours less. So JT was 2 hours less than RT, Roger's time. So how would I make them the same? So the time that Roger traveled, don't go that fast. Don't go that fast, Elias. You're getting ahead of me.
Judy was 2 hours less than.
Judy traveled 2 hours less. So in order for her to get there to travel the same time, we need to,
It would be Roger's time.
oops. Is that right?
No,
What's wrong with it?
you forgot the rates.
Okay, we're just looking at time right now.
Okay.
We haven't started rates. Is that right?
Yes.
Are those equal?
Yes.
So if, let's just put a couple numbers in here to find out. Her time was 5 hours. Roger's time was what?
What?
I'm just making up numbers. Just to
Oh,
look.
okay.
So if Judy's time took her 5 hours and it was 2 hours less than Roger's, how long did it take Roger? So how do I make these equal?
Add 2 to 5.
Add 2 to 5. So I added 2 hours to whose speed? Judy's.
Oh, yeah, I had it right.
So it's the time of Judy plus 2
Or did you do
equals the time.
Did you do the
Roger.
time of Roger minus 2?
Yes. So because Judy took 2 hours less, in order for it to be the same amount of time, we have to add 2 hours to her time. That seems to be the confusing part of these. Whenever something is less than another, making them equal. All right, so now we've got a whole bunch of information that we have to stick together in order to figure out the answer to. We've got this, this, and this. We also know that the distances were the same. So what the question is asking is, how far did they go? So instead of writing dr equals dj, we're going to write the rate of Roger times the time of Roger equals the rate of Judy to the time. Now we can start putting in, we can use substitution. And for RR, we can put in 12. For T of R, we can put in T of J plus 2 that we have right here. For RJ, what can we put in there?
20.
Oh, yeah, I've got that wrong. Yeah, 20. And for the time of Judy,
Time of Judy is.
you don't know that. Okay, so go ahead and see if you can find out the variable. What is the variable up there? What don't you know? Let's go ahead and write this. RR is 12. TR is time of Judy plus 2. What is the rate of Judy? 20 times the time of Judy. So what is the variable that we don't know? The time of Judy. Is that what we're looking for? No. We're looking for how far they went. We don't care about how long it took Judy, but you have to find out how long it took Judy in order to find out how far they went. So we've got distributing. Now what?
Minus 12.
Okay, now what?
Minus 20.
Minus 20?
Minus 12.
And what do I get then?
8.
I'm just kind of following your direction here. I get a negative 8 equals, okay, so my negatives disappear because they're on both sides there.
Positive.
So the time it took Judy is how long? 3 hours. So how do I find out how far she went?
Put that multiply by the time,
Okay,
or the rate.
because I know the distance Judy went is the rate times the time. The rate is 20, the time is 3. Multiply those two together and they went how far?
60 miles.
60 miles and you're done. Okay, bottom of page 105, example 22. You're in my English class. You will get this. Brer Rabbit hopped off toward the briar patch at 10 kilometers per hour.
Augusta.
So the time of Brer Rabbit is, oh, I'm sorry, that's not time, speed. I'm looking,
Mr. Ladder doesn't like you.
all right, what happened here?
It doesn't want you to teach this lesson. They got it.
People watch us.
Okay.
I feel this website.
I'm being smited. All right, the rate of the rabbit is 12. At noon, Brer Wolf began the chase from the same starting point.
Wait, where did you get 12?
Oh, I'm sorry, 10. Thank you. 10. Okay. The rate of Brer Wolf is what?
Unknown.
Unknown, that's what we're looking for. The time of the rabbit before he got caught was how far? Or how much?
2 hours.
When did the rabbit start?
9.
10. When did he get eaten?
9.
2. So how far, how long was he hopping?
4.
4 hours.
Sorry.
Okay. The time of the wolf. He started at,
Same spot.
okay, but what time?
2.
What time did the wolf start? Noon. What time did he eat Brer Rabbit?
2.
How long was he running?
2.
Okay. Was their distance the same?
Yep.
Yeah, they started from the same place. One just started before the other one did. So the distance of the rabbit is equal to the distance of the wolf. So the speed of the rabbit times the time of the rabbit equals the speed of the wolf times the time of the wolf. Plug in your numbers and find out how fast the wolf was running.
Oh, it's a keeper.
Last part of this section is similar triangles and proportions. This is what we've already done, so I'm just going to go real quick over this. Got a triangle here, got a triangle here, make it a little bit bigger. And this is 5, 7, and 8. And this is X, 9, and Y. And we're going to say that these angles are the same. Angle is the same as angle, so I only have to show the angles of 2 of them. All right, so as far as finding X is concerned, what numbers am I going to use?
5
7 and 9.
Okay, I'm going to say 5 is to X, the proportion of the same side, 5 is to X equals what? 7 is to 9. Notice we started on the left for the top numbers, the right for the bottom numbers, just made a proportion, cross multiply and you're done. Okay? So that's pretty much it for that.
So then for y, you do 8y equals, so that's
5.
8 over y. Yeah, that's
8 over Y equals 7 over 9, yeah. Yeah. Okay.
We've already basically had some of those tests. Wait, are we at a new lesson now?
Lesson 23 combined with lesson 22 here. This is going to be a really, really quick and simple lesson. I don't know why they put it as one whole entire lesson by itself, because we can pretty much do it in just a
Because
couple
I like
minutes.
wasting paper and making mistakes.
Okay, approximations. The only purpose for this lesson is in order for you to get a better idea as far as how graphs and equations work together. You will never use this as far as actually solving math problems because it's an approximation, it's not an exact answer. So, anyway, it does give you the skill of learning how to look at an equation and look at the graph and say, okay, yeah, that looks right. That's a pretty close approximation to what we've got there. All right, so what we're going to do is we're going to take a system of equations. At this point, well, one of the things you did in Algebra 1 is you learn this method first. It depends on the book, but the book I've taught out of, you learn this method first, and then you learn substitution and elimination. All right, so what this says is
that a 6 at the end?
that.
Yeah.
What else would it be?
I have no idea.
Gee.
So if you're thinking, what did you replace
The
with
original
79
unit.
must be
Is
6.
that excellent?
That's a -1 that just kind of, yes. We will learn exclamation points. Those are used in math. They're called factorials when you get into
Those-
statistics.
Oh, yeah.
I
Is
programmed
that
a
like,
calculator.
is that
Makes
like
you
the, if it's X?
Okay, anyway. Solve this equation by graphing. The way you do this, you take each equation, you put it in slope-intercept form. Go.
What?
Take each equation and put it in slope-intercept form. All right, what did you get for the slope-intercept form of 3y minus 2x equals 6?
Y equals 2/3 x plus 2.
Y equals what?
2/3 x plus 2.
And what did you get for y plus x equals -1?
Do that
Y
one.
minus x
Negative
minus
X.
Negative 1 minus.
That?
Yeah.
Sure, why not? I didn't have time.
Okay, so there are your two equations rewritten in slope-intercept form, the proper name for each one of your lines. So what I want you to do now is graph each one of those lines.
Oh, I was graphing it.
Okay,
That's why I
so
only
do
got
that
one.
right now. Okay, so there's the graph of both of those equations. What we're interested in is where those two lines cross. Because where those two lines cross, our x values and our y values are the same. So at this point right here, we are at like -3/2, +1. Looks like that's pretty close to where they cross. So where they cross, -3/2 and 1 share both lines. Okay, they have that one point in common. When you're solving a system of equations like this up here, when you're using substitution or elimination, you're finding a value of x and you're finding a value of y that work for both of those equations. When you show where those two equations cross on the graph, you're showing where the x and the y share the same value. So they're the same thing. So if you did system of equations with this, you would get x is -3/2 and y is 1.
Why is it actually factorial?
Well, whatever it actually is, I don't know. I mean, that's why I say it's just an approximation. You can't be exact with this because it's a graph and you're drawing it. So, anyway, the exact solution in the book is -9/5 and 4/5. Well, that's,
I have -2 and 1 works for me.
yeah, -2 and 1. So in an answer, Eric, on a test, I would take that answer because it's close. At least you have the right equations and the graph close enough that I can tell you get
It's
it.
not like 5 and 6.
Right.
So.
So that's pretty much as far as that lesson is concerned that they went over.
So you just kind of guess where they cross?
You're kind of guessing where they cross. Yeah. Yeah.
X